Welcome, this is Mr. Sutton bringing you the AB Calculus 4-6 lesson on graphical analysis. In this one, we are going to figure out some connections between the graphs of f, f prime, and f double prime. Before we can really use the connections between f, f prime, and f double prime, we need to review what those connections are. So using your knowledge of derivatives, see if you can fill out these charts below. All right, so for our first chart, we're talking about whether f prime, and f double prime are positive and negative and what that does for the other two of these. So if f is positive or negative, it doesn't really tell us a whole lot about what f prime or f double prime are doing. So, knowing whether the original function is above or below the x-axis doesn't tell me the slope, doesn't tell me the concavity. It just tells me where the original function is. So these are all going to be question marks because we just don't know without more information. Okay, now if f single prime is positive, well, that's going to tell us that we are increasing for the original function. And negative f prime means we are decreasing. But the relationship between f prime and f double prime is the same as between f and f prime. If we have a positive f prime, we don't know what f double prime is doing. Same thing with a negative f prime. Now we come to double prime. And if that's positive, we know that the original function is concave up, which I'll abbreviate there. And negative means we have concave down. Now it also means some things for f prime. Positive f double prime means that the thing it's the derivative of, f prime, must be increasing. And then that means f prime is decreasing if f double prime is negative. Now all these relationships work both ways. For example, if I want to know where f double prime is positive and I see an increasing f prime, well, I can make that connection there. All right, moving on to this other table. Now we're talking about what happens as one of these things goes from positive to negative. And we're not even going to bother putting in f positive to negative because that doesn't tell us a whole lot about anything here. But now if f prime is going positive to negative, that tells us that the function has a local max, assuming that the function exists at that spot. And then negative to positive, we've got a local min. Now what about f double prime? If f prime is going positive to negative, that at least tells us that it's decreasing. So f double prime ought to be negative. And negative to positive f prime means now we're increasing, so positive for f double prime. And we can do the connection another way. We know that if the second derivative is negative and f of c exists, then we have a max. Positive, concave up, we've got a min. So all these connections tie together here. That's what makes them connections. They're connected. All right, now what happens if f double prime is going positive to negative? Well, that means that we have a point of inflection on the original function, and it actually doesn't matter whether it's positive to negative or negative to positive. Either way, it's a point of inflection. And then it does make a difference for f prime, though. Positive to negative f double prime means we have a max on f prime, just like positive to negative f prime meant we had a max on f. And we have a min on f prime if we're going negative to positive f double prime. We're going to do a couple of examples now using all our connections. Pause the video and try this one out. We're just trying to match if a function has a negative f, f prime, and f double prime, which of these could the original function be? All right, so my strategy on these whenever I'm matching is process of elimination. Let's go through each of these properties. They said that f was negative. Well, that means visually that my graph has to be completely below the x-axis. So that means I can eliminate choice E, which is above the x-axis. Next, they said that f prime had to be negative as well. That means that f must be decreasing across the entire interval. Which of these graphs are not decreasing? Well, A is increasing and decreasing, so A is no good. And let's see here, C is just increasing the whole way, so also no good. B and D are both decreasing, so we can eliminate A and C, but we still have B and D in the running. Next, f double prime is negative. That tells me my graph of f is going to be concave down. So between B and D, which one is that going to be? Well, D is concave down initially, but then it becomes concave up, so we can eliminate D. That leaves us with just choice B. Here's another example for you to try out. This time around we have the graph of f prime, And we want to know, based off of this, on which interval the f graph, which they're not showing us, is decreasing. Pause the video, try it out. Now, when I'm looking for where f is decreasing, I'm basically looking for where f prime is negative. I notice that f prime is negative. This is the graph of f prime here. F prime is negative on the interval from 0 to 2, and also from 4 to 6. Therefore, I can conclude, if this were a free response, f is decreasing on those intervals, which gives us answer choice E. For this last final boss battle kind of question, we're given 3 graphs. One of them we know is f, one's f prime, and one is f double prime. The question is, which is which? Pause the video and see if you can put these in order of f, f prime, and f double prime. All right, let's see how that went. So my strategy when I'm doing something like this, because these are kind of tricky, is to pick a graph and try to spot its derivative. And specifically, I try to match up the number of maxes and mins in one graph with the number of x-intercepts in another graph. And then I look closer to see, if it's a max, is the other graph going from positive to negative kind of thing. So let's start with graph 1. Whose derivative is graph number 1? Well, we have an x-intercept here somewhere between -5 and -4, and we have another x-intercept over here between -2 and -1. So I'm looking for a graph that has 2 extrema, and exactly 2 extrema. Graph 2 does not. Graph 3, we've got a min down here and a max up here. So 1 could be the derivative of 3. Let's look a little closer. Right here, 1 is going from negative to positive, so that would be a min in the original graph. And we've got a min here. Nice. Let's just double check the other one. We're going from positive to negative between -2 and -1 for the x values. And hey, there's a max right there. So then 1 we can conclude is the derivative of graph 3. Okay, let's look at graph 2. Whose derivative is graph 2? Well, here again we have 2 x-intercepts, so that would suggest 2 extrema. We already know that 2 can't be the derivative of 3, so if 2's the derivative of anybody, it's got to be 1. So here at 3, we're going from positive to negative, so the original graph should have a max at -3. And graph 1 does in fact have a max there. We're going from negative to positive over here at x equals 1, so that means graph 1 better have a min down there, and it does. So this means then that 2 must be the derivative of graph 1. Let's look over here at graph 3. So graph 3 has 1, 2, 3 x-intercepts. So if graph 3 is anybody's derivative, the original function would have to have 3 extrema. Well, our other 2 choices here only have either 2 or 1 maxes or mins, so 3 is nobody's derivative. The function that is nobody's derivative must be the original function. So we know that we're starting with 3. 3 must be f. And what's 3's derivative? Oh, graph 1 was 3's derivative. So that means graph 1 must be f prime. And graph 2 was 1's derivative, so that means graph 2 must be f double prime. So that's it for this one. Till next time, this is Mr. Sutton signing off. This concludes our lesson on graphical analysis. Till next time, Mr. Sutton signing off.